Okay, students, we're going to talk about concept-centered geometry interim 2 test. Um, we're given these in the math collaboration meeting we had. In the above three here, there's 8 to 11 problems, all 1 point each. So most of the problems come from this. If I go down here, you see 2 to 4 problems on the above, but they count 2 to 4 points each. And then on the next page, we have, oops, that was it then, huh? What happened? I thought, was it good? Skip a page? There we go, skipped a page is what happened. Yeah. Okay, and then we have 2 problems from the above. They're 3 or 4 points each. Okay, so we're going to go through this here. All right, a dilation makes an object bigger or smaller. It takes a line not passing through the center of dilation to a parallel line and leaves the line passing through the center unchanged. Okay, so let's go to this right here. My content. Oh, what happened here? There we go. Okay. So let's say X and Y axis right there. What this is saying, say I have this line, take this line right like that. Okay, I can move it slightly so it goes right through there nicely. And if I say the center of dilation, so first off, I have to know from algebra 1 how to write the equation of that line in slope-intercept form. Y-intercept 1, 2, 3, so it's plus 3. The slope is up 1, right 1, so it's a slope of 1. So you can say 1x plus 3 or just x plus 3. That's the equation of that line. Okay. We're going to hit this again in mod 4. I'm just showing it to you now since apparently they might throw it on here in your mod interim 2 assessment, but it's in mod 4 that we'll be covering it. All right. So if I take a center of dilation right there that's not on the line, it says, it will give me a line that's parallel to it. So I have to know parallel means same slope. I have to know where I get the slope from. The slope is the coefficient of the x variable when it's written in slope-intercept form. So that parallel slope, that's my parallel symbol, of course, and there's my slope is 1. So that's not going to change. What's going to change is my y-intercept. So how far is it from here to here? 1. So every time I go 1 up, that's a dilation of now 2. It was 1. Now the total distance is 2. Remember, so we said dilate it 2. Scale factor of dilation is a scale factor of 2 with the center of dilation right there. Well, from there, there's 1. I double that, so that distance now is 2. So that now becomes my line. It's got to remain parallel. Oops, right here. So it has to remain parallel. Oops, what just happened there? Undo that. Do that. Okay, so I'm going to put total of 2 for dilation of 2. I have to draw a parallel line to that because when I do dilations, things remain parallel, always. Okay, since that center dilation was not on the line itself, it moved the line up to there. So now that equation is y equals x plus 4. Notice the slope is the same, but the y-intercept is different. Okay, now let's say this point, oops, let's go back to here. Let's say this center of dilation was now down here instead. Well, how far is it from here to here? A total of 2. So I'd have to go 2 again to right there to have a dilation of 2. If it was dilation of 3, I'd have to go 2 again, 1, 2, right up to there for another distance of 2, and that'd be a dilation of 3. Okay, so if it's a dilated 3, dilation of 3, or scale factor of 3. Also, dilations can be written as x comma y maps onto, in this case, 3x comma 3y. So remember we talked about rotations, translations, reflections. This is the rule for a dilation. The x and y get multiplied by the same number, whatever it happens to be, in this case 3, when a dilation of 3. So this is an example of a dilation rule. It's an example. Dilation rule. Example. Okay, so now what's the equation of that line? Again, it's got to be parallel. Okay, that can't change. Okay, so it's still going to be y equals 1x, but now the y-intercept is where? Well, 1, 2, 3, 4, 5, 6, 7, plus 7. Y equals 1x plus 7. Okay, that would be the equation. So that's what happens when it is, the center of dilation is not on the line itself. If the center of dilation was on the line itself, there or there, was actually on the line itself, it doesn't move at all. It's the exact same line. So just know that. The center of dilation is on the line itself. It's the exact same line, which then would be y equals x plus 3. Okay, so that's what and where's my, oh, prior to this here. Okay, so that's A. The dilation of line segments, so now we're talking about a line segment, not a line, is longer or shorter in the ratio given by the scale factor. So again, if it was double, it would be double in length. If it was triple, it would be triple in length. If it was a half, it would be a half in length. If it's longer, that's a line segment itself. Okay, I was going to say about triangles, for example. All right, number 2, given two figures, use the definition of similarity in terms of similarity transformations to decide if they are similar. Explain using similarity transformations the meaning of similarity for triangles as the equality of all corresponding pairs of angles and proportionality of all corresponding pairs of sides. So we have 3 ways of showing two triangles, for example, similar: SSS, SAS, and AA. Okay. So anytime it's dealing with the S, the side lengths, they must be of the same proportionality, also called the same ratio. Each corresponding side must have the same ratio from the pre-image to the image. So for example, if I had this triangle and this triangle, and I said that they were similar, and this length is 2 and this length is 4. This length is 7. This length must be what? That's the corresponding side. Well, the ratio is 1 to 2, or 2 to 4, which reduces to 1 to 2, so this must be a ratio of 1 to 2. 7 to 14, doubling it. Okay, if this was 6, then this would have to be 12. They all have to be the same ratio, 1 to 2 in this example. Could be whatever the ratio is, could be 2 to 3, 3 to 4, 3 to 5, but it has to be the same ratio on all S's anytime there's an S involved. Okay, if there's an A involved, the angles must be congruent. Okay, so if I had this triangle, I have this, and I have a bigger triangle, but those angles are now similar by AA similarity. AA similarity is also called AAA similarity. Why can they call it AAA? Because if the two angles are congruent, and remember all triangles add up to 180, then these third angles must also be congruent. And so that's why some books will say AA similarity, others will call it AAA similarity. They're the exact same thing. Okay, so there's 2 of the 3. Let me erase that. The last one is if it is SAS. So say I have this right here, and this is 40 degrees. This is 10, this is 15. So it's set up as SAS. So that means this would have to be 40 because the angles must be congruent. the sides must have the same ratio. If they told me that was 15, then I can see its corresponding side is 10. So 15 over 10, if I'm going this way, 15 over 10 reduces down to 3 over 2 because I divide each by 5. So that means this one, x over 15, would be my proportionality to have equal proportions. I could cross multiply 2x equals 45, divide by 2 and get 22.5, or I could say 2 times what is 15, and that's 7.5. So I multiply this by 7.5, and 3 times 7.5 is 22.5. Same answer both directions. So then this should have to be 22.5. Now they might go ahead and give you this instead. They say this is 22. And they ask, are they similar? Oh, there's my similar question mark. Are they? The answer is no, because it should have been 22.5 as we just showed right there by SAS. Okay, so that's how you check SAS for similarity. Okay, so that's number 2. Number 3, use the properties of similarity transformations to establish the AA criterion for 2 triangles to be similar. Okay, I'm doing similarity transformation. Let's take this right here, and here's my center of rotation, center of dilation limits. Let's change the color. All right, let's say I'm going to make it double. So whatever this length is, I go the exact same distance out, and there's my new point. Whatever this length is, I go that exact same distance out, and there's its new point. And then I would connect those. Okay, well, don't forget with similarity, if, as we saw before, if I'm dilating some figure segment, for example, the lines will remain parallel. So it's going to remain parallel. Okay, well now if you look at parallel lines cut by a transversal, first off, this angle is congruent to itself because it would be like in both triangles, but in the small one and the big one. But since I have parallel lines cut by a transversal, these corresponding angles are congruent, and these corresponding angles are congruent. So in that case, I'm talking about these. If I was talking about these triangles here, say I made it into a triangle and dilated it, I would have the AA similarity for triangles. Okay. So don't forget, from the center of dilation, the lines remain parallel and angles must be congruent and the side lengths must be proportional or the same ratio. That's what you need to know for similarity. Okay. All right. So it's going to be 2 to 4 problems of these. Proof theorems about lines and angles. Theorems include vertical angles are congruent. You should know that. There's an example. Vertical angles there. Vertical angles there. You have alternate interior angles are congruent. If those are parallel lines cut by transversal, then I have 1 and 2 is congruent, alternate interior angles. 3 and 4 are congruent, alternate interior angles. Corresponding angles are congruent. If I have parallel lines cut by a transversal, 1 is congruent to 5, 2 is congruent to 6, 3 is congruent to 4, and 7 is congruent to 8. Okay, those are my corresponding angles. Corresponding angles are congruent. Points on a perpendicular bisector are equidistant from the endpoints. Okay, here's a segment. Here's its perpendicular bisector. It shows it's a perpendicular bisector of that segment AB. What this is saying is any point on this perpendicular bisector is equidistant from the endpoints. That distance is equal to that distance. If I go from this one, it's also on the perpendicular bisector. That distance is equal to that distance. That's all it's saying. Any point on the perpendicular bisector is equidistant from the endpoints, from the segment's endpoints. Proof theorems about triangles. Measures of interior angles of a triangle sum to 180. Base angles in an isosceles triangle are congruent. That's the isosceles triangle theorem. Remember I told you the very first thing you see whenever you see an isosceles triangle. If I saw that isosceles triangle, don't forget that's called a vertex angle. Automatically, first thing I'm going to mark on my base angle is congruent, and that is the isosceles triangle theorem, which says if I have an isosceles triangle, then the base angles in an isosceles triangle are congruent. Okay, the segments join the midpoints of two sides of a triangle. So if I do the midpoint of these now, say that equals that and that equals that, then these are called midpoints. They're right in the middle of that segment. If I connect the two midpoints, it will be parallel to the base there. So that means that is parallel right there, and it is 1/2. That's x. This is 2x. So it will automatically be 1/2 of it. Okay, you're going to see that on the DCAS. Let's see, what else is next? The medians of a triangle. Okay, so medians. Our definition of median. Median goes from the vertex to the midpoint of the opposite side. Vertex to the midpoint of the opposite side. Okay, vertex to the midpoint of the opposite side. They all intersect in that point right there called the centroid. Okay, that's the centroid. Then we have these segments of the centroid. This segment is 2x, this segment is 1x. So the longer segment of the two is double the shorter one. Well, the shorter one is half the longer one. And of course, then the total length would be 3x, or it's divided into 3 parts. If you want. So this gets 1/3. X is 1/3 of the whole length. This is 2x over 3x is 2/3 of the whole length. And always the whole length is 3x. Okay, centroid. Proof theorems of parallelograms. Okay. So if I have a parallelogram, the definition of parallelogram is a quadrilateral with opposite sides parallel. That's why you see the word parallelogram. Okay, so what are the characteristics that are true? Opposite sides are congruent. So that's congruent to that, that's congruent to that. Opposite angles are congruent. That angle is congruent to that angle. This angle is congruent to this angle. This is for all parallelograms. And don't forget, underneath parallelograms, we have rhombus, rectangle, and squares. This is true for all rhombus, rectangle, and squares as well. The diagonals of the parallelogram bisect each other. Let's change the color. So that diagonal, this diagonal bisects the other diagonal. So that equals that, and that equals that. The diagonals bisect each other. And conversely, rectangles are parallelograms with congruent diagonals. Rectangles below the, we have rectangle over here, rhombus over here. Our quadrilateral hierarchy theorem that I've given you, rhombus, rectangle, and then you put those two together and you get square at the bottom. Okay, it's going to be these ones that they mainly focus on. So you want to make sure you have that. So what they're saying, the rectangle is all those characteristics on that parallelogram and 2 extras. These are all right angles here, and that these diagonals not only they bisect each other, but they're congruent. And that's what it's saying right there. Those diagonals are congruent. Not only they bisect each other, but they're both the same length. Okay, remember rhombus, definition of rhombus is a parallelogram with 4 congruent sides, and a square is a rhombus and a square rectangle put together. So the rhombus part, square has 4 congruent sides, and the rectangle part, 4 right angles. So square has 4 right angles. Okay, so that's reviewing all of that right there. 2 to 4 problems on that, 2 to 4 points each. Remember, the 5 sufficient conditions at the bottom of your quadrilateral hierarchy sheet. Remember, this is to prove a quadrilateral is a parallelogram. If one of those 5 is true, which these 4 up here that they just listed, plus the 5th one, remember the 5th one was if one pair of sides was parallel and congruent, then it's a parallelogram. So all those plus that fifth one plus the four here that we just mentioned right here, okay, about parallelograms. If any of those four come out to be true, so if they show me both pairs of opposite angles are congruent, then it's a parallelogram. If the diagonals bisect each other, then it's a parallelogram. If both pairs of opposite sides are congruent, then it's a parallelogram. Okay. And if consecutive angles are supplementary, okay, if both pairs of consecutive angles are supplementary, also called same side interior angles, then it's a parallelogram. Those are the five sufficient conditions. That means they suffice to make it a parallelogram. If any one of those five occur, then the quadrilateral is a parallelogram. You can call it one of the five sufficient conditions. Okay, next page. Another precise definition of angle. Remember, an angle is two rays that share a common endpoint. Circle is all points that are equidistant from a certain point called the center in a plane. Remember, if it's in space, then that's a sphere. That's the difference between the definition of circle and sphere is one is in a plane, one's in space. Perpendicular line means 90 degrees. So there's perpendicular lines. Parallel lines, remember that means same slope, don't intersect, and also in the same plane. Remember, if they're not in the same plane, two lines that don't intersect that are in space are called skew lines. Okay, such as in parallel and skew. Parallel is in the same plane, skew is in space. Line segment, two endpoints and all the points in between them. Okay, undefined, the three undefined terms in geometry, point, line, and what's the third one? Why do I forget that? Point, line, not plane, is it? Is it point, line, and plane? It's on your decast sheet. Point, line, okay, I forget the third one right now. Represent transformations in a plane using transparencies. Okay, we didn't do that. We did it by hand. Given a rectangle, parallelogram, trapezoid, regular polygon, describe the rotations and reflections that carry it onto itself. Okay, remember to find the degrees, a regular polygon deals with regular polygons. That's what you're going to see on the decast. It's a regular polygon. Okay, it's 360 divided by n. N being the number of sides or number of angles. That is the first angle of rotation. If they only want one, it's always that first one. If they say angles of rotation, then you name all of them up until you hit 360 degrees. You do not include 0 or 360 in it. Okay. And every time it rotates, again, this is true for regular polygons, not just any normal. Remember, regular means equilateral and equiangular. Develop definition of rotation, reflection, translations in terms of angles, circles, perpendicular lines, parallel lines. Okay, segments. Remember, rotation is two reflections over intersecting lines. A reflection is a single reflection and it switches orientation. Translations are two reflections over parallel lines and they keep the same orientation just as rotations do because there's an even number of reflections. It keeps same orientation. Remember, orientation is either clockwise or counterclockwise. Let's see. Draw a transformation graph here using specific sequence of transformation. So carry figure on to another. Okay, that's going from the pre-image to the image. That's our rotations, reflections. What's our transformations unit? You need to know rotation of 90, rotation of negative 90, which means clockwise 90 degrees, or positive degrees is counterclockwise, negative degrees is clockwise. Rotation of 180, rotation of 270 or negative 270 being the same as negative 90 and 90. All on your decast sheet there. Okay, understanding congruence in terms of rigid motions. Remember, another name for rigid motions are isometries. You need to know that. They use both terms on the decast. A rigid motion is either a reflection, a translation, rotation, glide reflection. Usually they don't focus on glide reflection, they focus on reflection, translation, rotation. Remember, that means anytime I can go from the pre-image to the image by one of those combinations, then that is the definition of congruence for the DCAS. You need to know that. It's guaranteed to be on there. I can go from the pre-image to the image by any combination of rigid motions / isometries. And then also have a pre-image and image and say, how did it get from the pre-image to the image? You have to be able to identify what it got reflected over, or whether it got translated so many units, or it got rotated. Okay, and those are usually multiple choice questions to choose from, see which one works, or which ones if there's more than one. Use definition of congruence in terms of rigid motion to show that two triangles are congruent. I just talked about that. If and only if corresponding pairs of sides and angles are congruent. Explain how the criteria for ASA, SAS, and SS fall from the definition of congruence, because all the angles and sides, corresponding angles and sides, are congruent. And I can get from the pre-image to the image by a combination of rigid motions. Prove geometric theorems. Theorems include vertical angles. Okay, we already went through that. The one we didn't talk about is proving the sum of the interior angles of a triangle is 180. I'll see about possibly doing that. We did not focus on constructions this year, so we told they weren't. I will show you, send out the videos on how to do those right before the DCAS and or right before here as well. Okay, so let me quickly see about proving the angles of a triangle, add to 180. So if I have 1, 2, 3, 4, and 5, and this is parallel to this. Okay. So simple proof. Okay, remember statement, reason. Reason is also called justification. It used to always be called justification. Okay. And we'll call this line N is parallel to segment AB, given. Okay, 2. Measure of angle 1 plus measure of angle 2 plus measure of angle 3 equals 180. Definition of straight angle. Okay, remember, anytime the angles create a line, as angles 1, 2, and 3 create, and they're adjacent to one another, that is 180 degrees. Okay. Next, I know that angle 3 is congruent to angle 5, and angle 1 is congruent to angle 4, don't I? Remember I said, whenever the first thing you should be thinking, parallel lines cut by transversal, the very first thing you should be thinking is AIA. AIA theorem. Talked about this. So you can see alternate interior angles there and alternate interior angles there. Okay. Then the measure of angle 3 equals the measure of angle 5. Measure of angle 1 equals the measure of angle 4. Definition of congruence. So if two angles are congruent, as we set up here in 3, then they have to have the same angle measure, and that's from definition of congruence. Lastly, I can now substitute those in there. So now I can say the measure of angle 4 plus the measure of angle 2 plus the measure of angle 5 equals 180. And that is by substitution. I substituted those in there. And there's a proof right there. And they've had this on for years. So memorize this proof. And the DCAS, well, off and on for years, they've had it. I've seen it multiple times, is my point. So that's how you'd prove the angles of a triangle add to 180 degrees. All right, that does it, 29 minutes.